Hello again and welcome to another video lesson with Lawson. Today we're going to start looking at inclines. We will be taking a much closer look at inclines when we're working through the forces unit a little bit later in the curriculum. But right now we're just going to look at how we could describe motion as something slides up or down an inclined plane. When we have an object on an incline, the first thing to realize is all it means is that there's a gradient or there's some kind of angle between the horizontal and the surface. Because there's an angle between the horizontal and the surface, it makes it so that an object sitting on that surface is likely to want to slide or roll down that incline. In this case, we see that the incline is a slope that would cause this block to want to slide to the left. It is possible that it's not moving. If there's enough friction present or some other force, either by a rope or something that's stopping it from sliding down, then it won't. If nothing's acting on it and there's no friction to prevent it, it will start sliding down this slope, and we would want to be able to describe the motion if it does. One of the first steps to being able to simplify this motion is realizing that since it's moving along that surface in one single direction, this is really just another example of one-dimensional motion. Kind of like free fall is an example of one-dimensional motion with a special circumstance where the acceleration is already known. When a mass is moving along an incline, it also is one of those situations that's just a specialized one-dimensional motion. The acceleration experienced by this block will be a percentage of the acceleration due to gravity. If the incline was steep enough, if that angle was 90 degrees, where it was just simply sliding down a flat surface perpendicular to the ground, then it would accelerate at 9.8 meters per second on Earth, or at the rate which the gravitational field it's in would cause it to want to accelerate. In this case, we don't know exactly what the angle is, but we know it's some angle theta. And initially, when we're thinking about our normal coordinate systems, we might think that this is a difficult problem because it's moving in both the x and the y direction. But there's a simple strategy we'll use to simplify the motion. Let's take our horizontal axis that's parallel to the ground. And we can see as we move to the left along this axis, that's the negative relative to the origin of the starting position. As we move to the right, that's the positive direction relative to the origin, or our starting position in this case. Currently, it doesn't really line up with the motion well, so we just simply have to create a little bit of rotation to our axis, and we're going to actually rotate it so that it is parallel to the surface of the plane. Now we can see very easily that the block moving up or down this incline is actually moving right along that axis, or right along that coordinate system, and that makes it relatively easy to identify the position at any given point in time. And if we know as time's going by what the position is, we can also identify our other kinematic variables, things like its velocity at a different point, or the time it takes to get to a specific point, or the acceleration that the block is experiencing. Although the acceleration is one of the more easy parts of these types of problems, which we'll get to in a moment. If you look carefully, as we took that horizontal axis and rotated it so that it was parallel to the surface, we had to rotate it the same number of degrees that the ramp itself is relative to the horizontal surface. So it turns out that the angle here that's created between our coordinate system and the horizontal is exactly the same as the angle here that is created by the incline or the ramp on the surface. We could just as easily have made down the ramp positive and up the ramp negative. Being able to determine how we want to use a specific coordinate system is one of the ways we can simplify some problems. If we only had this block sliding down the ramp, making the direction that the block moves down the ramp the positive direction can reduce the number of errors that might be made. When looking at incline problems, there's essentially two situations. You're either going to have an incline that's frictionless, which means there's no friction present. That's going to be shown as you see here with the Greek symbol mu. That mu is related to friction forces, and when we do our forces unit, we'll elaborate on that. But for now, understand that if you see an incline where it shows the symbol mu being equal to 0, that's just another way of saying that's a frictionless surface. It's also likely you might see that and see this is a frictionless surface, or there's negligible friction, or consider without any friction forces. When a block is on an incline and there are no friction forces to be able to stop it from sliding or moving, it will always slide down towards the bottom unless it's got some initial velocity going up the incline. Then it will continue going up the incline until it either goes over the edge or until it comes to a rest and then slides back down the incline in the direction that it was coming up from. Either way, regardless of how it might happen, the acceleration is always the same value on these frictionless inclines. it's going to be g sine theta, where g is the acceleration due to gravity, and theta is the angle that the incline makes with the horizontal, or the angle that it's necessary to rotate our coordinate system so that it is parallel to the surface of that incline. That acceleration is down the incline, so if we make down the incline positive, that's a positive acceleration. If we make down the incline negative, then that's a negative acceleration. Given that the acceleration is essentially a known value or based on some constants of the situation, what we really have to look at is whether or not we're imagining a block being pushed up with an initial velocity and seeing how high it goes before coming to a stop. Then we'd know our final velocity is 0. Or if a block's sitting at rest and released and we know our initial velocity is 0, how far it slides to reach a certain speed, or how much time it takes to reach the bottom, or any other combination of the kinematics variables. We could also be given the height of this ramp and either the length of the surface itself or the horizontal length of the ramp. Any way that they give us 2 of the 3 parts of this triangle that forms our inclined plane, that would allow us to be able to find the angle theta as well. Don't forget about your right triangle math, because that will be useful for some of these problems. While we can have frictionless inclines, we can also have inclines where the mu is not equal to 0. Friction is not negligible or ignored. It turns out that while the acceleration is constant when it moves in one direction, the acceleration as a block slides up the ramp is different than the acceleration of a block that slides down the ramp when friction is present. We can find the acceleration parallel to the surface of the incline relatively easily. We still use g sine theta just like we saw on the frictionless incline. However, when the block is sliding up the ramp, friction, which is opposing its motion, is also going down the ramp. And so gravity and friction are working together in that case, and they actually increase the rate at which you decelerate as you're going up, or they make it so that you slow down in a shorter distance and with a shorter time. A block sliding up the ramp, you would use the g sine theta plus mu g cosine theta to be able to figure out the acceleration in the direction down the ramp when the block stops and starts to slide down the ramp, or if the block is released from rest on the ramp. Gravity is pulling it down the ramp and causing it to accelerate as it slides down, but friction is opposing the motion and pushing up the ramp or trying to stop it from sliding down. And it's because they're going against each other that when you have a block sliding down a ramp with friction, we would get the acceleration in the direction down the ramp by taking g sine theta and subtracting mu g cosine theta. What determines whether or not you add or subtract those 2 values is whether or not you're sliding up or down the ramp. And even though moving in one direction has a constant acceleration, moving up a ramp with friction versus moving down a ramp with friction, you would expect 2 different acceleration values. On a frictionless incline, it turns out to be the same. If you push a block up at 4 meters per second, when it returns back to that point, it'll be going 4 meters per second in the opposite direction. But when there's friction present, it'll actually make it so it's no longer symmetrical motion, because you no longer experience one single acceleration for the entire motion. You can break it into 2 parts and do a UAM situation where you have acceleration sliding up the ramp and then the acceleration sliding down the ramp, and treat those as stage 1 and stage 2 to be able to describe the motion anywhere along there.